record on this computer. I hope you can all hear me. And the chat room is open, and so feel free to chat. Because of these damned FERPA rules, you should chat anonymously. Let's see, what is this? Everyone. Okay, anyway, let's start by going to the place where we left off last time. Maybe I should instead go back a little bit and remind you that we derived something called a Laurent series, or a Laurent series, if you want to use the French pronunciation, my approximation to the French pronunciation. What we did then, you remember, is that we considered a function that had various singularities, and we did a contour integral that was zero because it didn't include any of the singularities, and could be shrunk to a point, and so it's a zero integral. And so we were, well, I shouldn't say it was a zero integral, because we were integrating 1 over z prime minus z around the contour. And so we got f of z. We massaged the denominators and wound up with a difference of 2 infinite sums. And these converged absolutely and uniformly because the points on curve C1 are, or I should say Z is closer to the points on Z1 than Z0 is. And on the other hand, actually, let me re-say that. On C1, Z prime minus Z0 is greater than Z minus Z0. And over here, Z minus Z0 is greater than Z double prime minus Z0. Was there a question? Anyhow, we then wound up with one huge sum from minus infinity to plus infinity, and we wrote this in the conventional way, which is to call this integral the residue, the nth residue at Z0. And I'm not sure everybody uses exactly this terminology, but I'm going to use it. And so this is the nth residue, and we get this sum then from minus infinity to plus infinity. Now, normally, if you have a nice function, there are no terms with negative n, or if there are terms with negative n, you might have minus 13, but you don't go down to minus infinity. But you do if you have an essential singularity. Now, actually, the usage that's more common is that a sub minus 1 is called the residue of the function at Z0. And we'll see why that one is particularly noteworthy a little bit later. Notice that these residues, a sub minus L, you can often get if the series goes from minus L to infinity, then you can get the residue a sub minus L by taking the limit z minus Z0 to the L f of z as z approaches Z0. Because what will happen is the worst singularity will cancel, all the other ones will be positive. values of positive powers of z minus z0, and consequently, the one that you'll get is this one here. The other ones all go to 0. You can also have a more elaborate recipe to get the one that's at not minus L, but minus L plus 1. And then what you do is you first cancel the singularity at minus L, and then you look for the minus L residue, and so forth. Okay. Actually, I think we already did this, so this is a review. A function that's analytic for all z is entire. A function that has an isolated singularity has an isolated singularity if it's analytic in a disk around z0 but not at z0. And pole of order n is a function that's such that z minus z0 to the nf of z is analytic at z0, but if you use one less factor, one fewer factors, you get an isolated singularity. A pole of order 1 is a simple pole. Poles are isolated singularities, and a function is meromorphic if it's analytic, except for poles. Here's an example of a function that's meromorphic. It has a pole of order j at the point j. An essential singularity is a pole of infinite order. Here's an example of an essential singularity at 0, e to the 1 over z. These things do occur in physics. Okay, there was a question here. Is residue related to Gibbs overshoot? It may be. I don't see the connection immediately, but maybe there is a connection. I'd have to think about that, and I think instead of thinking about that, I should just go on with the lecture because I don't have nothing occurs to me immediately. Here's a meromorphic function with 2 poles. F of z is 1 over z times z minus 1. And of course, we can do that as an infinite sum, a Laurent series. If we look at a sub n, well, it's just given by this integral. And this integral this integral is the recipe that we saw earlier when we were talking about this kind of series, namely that the residue, the nth residue at z0 is an integral of f of z around the point z0, and you divide by n plus 1. All right, so let me get back to here. And so, so this is an example. I often skip examples, but I think maybe it's worth doing some here. So if we look at the nth, the coefficient a sub n, it is this integral, and it's a counterclockwise circle, radius less than 1, and we can expand 1 over z, 1 over 1 plus z as a power series, and we get this power series, and consequently we can rewrite this as a power series like that, and then we see it starts at -1, and that's because it's meromorphic with just a simple pole at z equals 0. Here's an example that those of you who like this subject. I think maybe I should do this on Wednesday if you want to see it. But the idea is G of Z is just has a simple form and a pole of order. Well, it depends on what n is. And all right, so let me go to analytic continuation, and here let me I actually, let's see, how do I minimize this damn thing? Let's auto minimize and at least to make it smaller. And so this is a continuation of the example PDF that is on the class website. So the idea with analytic continuation is that you might have a function that's analytic in a circle of radius r about, in a disk of radius r about the point z0, and suppose the nearest singularity is z prime. So pick a point z1 over here and then do a power series expansion about z1. Hold on, there's a, okay, a pole. So there was a question about a pole. So let me just, all right, there's a little bit of space here and I'll say something about a pole. 1 over z minus z0, that's a simple pole at z0. 1 over z minus z0 cubed, say, is a pole of order 3 at z0. So that it's just a singularity that looks like that. Somebody wants me to do example 6.14 today. What is 6.14? Oh gosh. All right, well, since there is a request, all right, I'll do it. So suppose we've got a function that's analytic in a certain simply connected region R, and we've got a contour, a closed contour that lies inside the simply connected region. F of Z is analytic in the region, G is meromorphic. And what we're going to do is we're going to say, that G of Z has just this very simple form. So then we take the ratio of G prime over G. Well, the derivative of G is just NZ minus W to the n minus 1. And we divide by Z minus W to the n, and I let the coefficient A sub n of W just cancel. So this is just n over Z minus W. That's a simple pole. And so if we shrink this contour C so that it's only around the singularity at W and make it a tiny integral around that, or actually we don't even need to do that because F of Z is analytic. So this is in Cauchy's integral formula tells us that this is n. We pull out the n, what's left is just F of W. That's Cauchy's integral theorem. If you have a meromorphic function, you're going to have a Laurent series like this, and you've got, we're summing here over all the powers. So we're doing the series around W. And then it turns out if you do this integral, you get n sub L F so of WL. So that's an exercise. So I'm going to skip that since it might be a homework problem. So to get back to this analytic continuation, which is really important, the idea is that we have a function that's analytic in a certain region, and in particular, we can do a power series about radius r, and so we have analyticity within this circle. And suppose the nearest singularity is at z prime. So we can do another power series expansion of the function around the point z1. And for sure, it'll converge within the green circle, but it might converge also within the blue circle. And in that case, we've discovered that the region of analyticity for the function is not the disk of radius r, but it's that disk plus a little wedge here so we've got a larger region of analyticity. And it turns out that, of course, you know, you have all kinds of functions. There are infinitely many functions. The functions that are most important are the nice functions. And the nice functions are such that typically when you do analytic continuation, you get to be able to do quite a bit of extension. In other words, you can extend the region of analyticity in a in an impressive way. The most striking example is the power series about zero of just z to the n. And we know this for absolute value of z less than 1, this converges and defines an analytic function inside a circle of radius 1. On the other hand, we can sum the series. Within the circle, it's 1 over 1 minus z. But now we've defined a function that is analytic everywhere except at the point 1. And so we've extended the function f of z from a circle of radius 1 to the whole complex plane except for the point z equal to 1. And so that's a striking example of analyticity. Another example is the gamma function, which is defined like this. And I see I didn't leave enough space to talk about the gamma function, so I understand it's possible for me to move this stuff down, but I don't know how to do that. So I'm just going to go down here and just remind you of what the gamma function looks like. This gamma of z, what we can see here is that if z is equal to 0, we've got a singularity here in T. And so it's analytic to start with. If we've got the complex plane like this, it's analytic to start with in the right half plane. But on the other hand, we know that there's this fundamental identity with, well, let's see, let me try to show you guys the whole thing. There, that's going to get obscured. So let me move this over. We know that the gamma function has this important relation, namely that gamma of z, that z gamma of z is gamma of z plus 1. And so that means we can write gamma of z as 1 over z gamma of z plus 1. But now gamma of z plus 1 is analytic as long as z plus 1 is in the right half plane. But that means that we've now got analyticity in a larger region. So this is the point -1. Over here we had 0. Now we have analyticity also in this region. And then we play the trick again and we say, well, gamma of z plus 1 is 1 over z plus 1, gamma of z plus 2. Now we have analyticity in a yet larger region, which is just the region to the right of -2. And so now we have a bigger region. Well, you continue in this way, what you find out, whoops. What you find out is that the gamma function, so let me go back to 0. The gamma function is analytic in the complex plane apart from the points 0, -1, -2, -3, and so forth. So it's analytic in the whole complex plane apart from the negative integers and z equal to 0. So that's an a less trivial, a very impressive example of analyticity. I think we can certainly skip those examples and now go to the calculus of residues. And the idea here is that we have an analytic function, and we know that the analytic function of the integral of an analytic function along a contour doesn't change unless the endpoints change or move, or the contour crosses a singularity or leaves the region of analyticity. And so let's consider the integral of a function along a counterclockwise closed contour that encircles n poles of a function f that's meromorphic. So we've got a simply connected region, the function is meromorphic. And what we're going to do then is we're going to shrink the contour without changing the value of the integral until the area is infinitesimal and the contour is just a sum of n counterclockwise circles around the n poles. And so let me do as an example one of these. And what I did over here is let's suppose that we have a pole of order n in this function f of z, and we're going to do the integral around that contour. So I could have written this as c, whoops, why am I, well, what the hell, c sub minus n. That's the contour. And what we're going to do then to do the integral is we're going to just do a tiny counterclockwise integral around z0. We set z equal to z0 plus epsilon e to the I theta. dz is that. And then we translate all this and it becomes an integral from 0 to pi, 0 to 2 pi of d theta. dz is I epsilon e to the I theta d theta. Z minus Z0 is just epsilon e to the I theta. So we've just got this structure here. And now one of the epsilons cancels and we have 1 over epsilon to the n minus 1. We can bring out the constant factor. We bring out the I. What we have left is an integral from 0 to 2 pi d theta e to the I theta 1 minus n. Well, here we dodge a bullet because this integral is 0 unless n is equal to 1. And if n is equal to 1, we're just integrating 1 from 0 to 2 pi, and that's just 2 pi. So the answer is that we get 0 unless n is equal to 1. Well, if n is equal to 1, the denominator is just 1. And we have 2 pi I a minus 1 of z0 delta of n and minus 1. So that's the heart of the residue theorem. It means when you do this integral, what you wind up doing is you look at the function and the series, the Laurent series of the function at each of the points where it has a singularity, and you do the integral, and the only thing that survives is this a sub minus 1. And these a sub minus 1s are what are called the residues. The other ones turn out to be 0 in this case. And in particular, if the function f of z is particularly simple, just as a simple pole, then we can find the value of a sub minus 1 like this, and alternatively, we can just say a sub minus 1 is just this integral, and it's just the integral of f around the singularity, and the singularity is 1 over z minus w. Anyway, here's another example, and this is one that has just simple poles, and if we integrate along a circle of radius 2, we wind up with a sum that looks like this, and it's 1 over, it turns out to be the zeta function. And another example just gives you Cauchy's integral formula, namely that if you consider the function to be f of z over z minus w, then this is 2 pi I a minus 1 of w, which is effectively this, and that's 2 pi I f. So it's Cauchy's integral formula again. As I said to you early in the course, well, in the chapter on analytic function and functions of a complex variable, everything is just tightly related. It's like a game of dominoes. Actually, though, I've never played a game of dominoes, so I don't, or if I did, I was a child and I've forgotten. Anyhow, let's look at this particular example. Here's a meromorphic function. It has a simple pole at z equal to 1 and a double pole at z equal to 2. And we're going to integrate it along a circle of radius 4 about the origin. And so what do we get? Well, we then shrink it down, and the residue theorem tells us, well, it's going to be 2 pi I times the residue at minus 1, or what I might call the principal residue. Anyway, the residue at minus 1, and then the residue at 1 and the residue at 2, because it has 2 singularities here. And it just has a simple pole at 1, and so we can either use the formula 6120 to find the thing, find the result, and then we get the limit z goes to 1 of 1 over z minus 2, and that's just 1. On the other hand, we can use the standard definition of the residue and do the integral around the pole at z equal to 1, and then we again get 1 by Cauchy's integral formula. If we look at look for a minus 1 of 2, then the standard way to do that is to do, well, is to do by definition, it'll give us, by the residue theorem, it should be this integral. And by Cauchy's integral formula, we can just compute it very easily. It's the second derivative of this function at z equal to 2, and so we get minus 1. And on the other hand, we would get the same answer if we had used this recipe, multiply by z minus 2, and we get that. And then to get the a minus 1, we use that more complicated formula, and we get minus 1 as the residue at 2. So the actual integral is then the sum of these two residues. One of them is equal to 1, the other one is equal to minus 1, so we get 0. Now, the function, once again, is this, and now we can say, well, there's an easier way to do this, because instead of integrating around a contour radius 4, we can integrate along a contour radius capital R, where capital R is some huge number. And in that case, the function goes down as 1 over R cubed. The perimeter goes up as R, so the whole integral is 1 over R squared. The limit of that as R goes to infinity is 0. So we again get the answer 0, but without doing any work. This is an example of what I call a ghost contour. Okay, there's a question here. Why are there no other values for n other than 0 and 1? What was 0 and what was 1? I'm a little confused about the question. The puzzling thing about the residue theorem is if you have this meromorphic function that has simple poles, double poles, triple poles, pole of order 13 in the region, and you shrink the contour around each of those singularities where you've got just an isolated pole of order k or whatever, the order n sub k. The surprising thing is that the only thing that shows up is a sub minus 1, which is the principal residue of f at that point, zk. And the reason for that is what I went through here, namely that if you have a higher power of z minus z0, it doesn't matter. It vanishes unless little n is equal to 1. So I hope that's the reason why people like this theorem. The surprising thing about it is that all the scary singularities don't matter, and we just need to find the principal residues, add them up, multiply by 2 pi I, and that's the actual value of the integral. Okay. I hope that's okay. Now, I like this term ghost contour, and the idea is that sometimes you're going to integrate a function. In fact, very often, most often in physics, when you're supposed to integrate something, we have an integral along the real line, and it goes from one point to another point on the real line. Frequently, it's an integral along the whole real line or half the real line. And the question is, well, what can we use analytic function theory to evaluate the integral? And sometimes we can, and the cases when we can are typically when we, so let me draw a picture of this. So let's suppose, in other words, that we're told that we, this is sort of a new topic. We're told that we're supposed to integrate from here to there along the real axis. And sometimes we can add a contour along which the integral of the function actually vanishes. And then we've converted the problem into an integral of the function along a closed contour. Now, normally this typically occurs, or the most frequent case where it occurs is where the integral is along the original integral is from minus infinity to plus infinity. And it's a pretty lousy infinity, minus infinity to plus infinity. And then what we often do is we add a contour like that in the upper half plane, or we add a contour in the lower half plane. Notice that the original contour is from minus infinity to plus infinity in the positive direction. And so actually, I made a mistake here. If we add the ghost contour in the upper half plane, it's counterclockwise. But if we do it here, let's see if I can fix this. All right, so well, I sort of fixed it. Okay, here's the contour in the lower half plane, but now we're going to integrate this way because the original integral was like this, from minus infinity to plus infinity. So it's useful to do this when the extra contour, the green contour, is a contour along which the integral of the function vanishes. So the best way to see this is to see this with a concrete example, and a nice example is example 22 here. So suppose we're trying to do an integral from minus infinity to plus infinity, and the function is 1 over x minus I, x minus 2i, x minus 3i. So this is a function that has 3 simple poles on the imaginary axis. And in fact, if I then draw a picture here, what we've got is we've got a singularity here, a singularity there, and another singularity there. And we're supposed to integrate from minus infinity to plus infinity along this real axis. And one thing we can do is we can say, okay, we're going to add a contour, and the contour is going to go like this. And so now we've converted it to a closed contour, which we can then shrink around the to 3 closed contours around the 3 singularities at I, 2i, and 3i. And because this is a circle of radius capital R, which is, we're going to let capital R go to infinity. So I here, let me switch to say black, the value of I along the contour, so along the green contour, so along this contour, the integral of f of z dz, an absolute value, is something like 2 pi capital R over R cubed, because there are three, because f of z is 1 over z minus I, z minus 2i, z minus 3i. So z has the value R, or a value, the magnitude of z is, the absolute value of z is equal to R on this contour here. And so this goes to, so the limit of this is 0 as you let R go to infinity. And you have to let R go to infinity because in order to close the contour, you have to go, you take the limit from minus R, you take the integral, the integral is defined as a limit from minus capital R to plus capital R of f of x dx, but you're taking the limit as capital R goes to infinity. So then you add a contour that is z equal to big R e to the I theta. Theta going from 0 to pi, and so you get this green ghost contour. And on that contour, the function is the absolute value of the function is approximately 1 over capital R cubed, and so there's no contribution at 0. And so you can then shrink the contour to tiny ones around I, 2i, and 3i, and you can compute them using Cauchy's integral formula. On the other hand, there's another way of doing it. We could have added a different contour. Namely, we could have added this contour. And when we add this contour, we see we don't encircle any poles at all. And so we get that the value of the integral is 0. So the result is I equals 0. And we can get that result by adding the ghost contour in the negative half plane, and we do that. We get the answer just by Cauchy's integral formula or Cauchy's integral theorem. Since the function is completely analytic in the lower half plane, we get the integral of a closed contour is 0, and so we get that result without doing any work at all. We just add the ghost contour. So the only thing to check is that the contour is a ghost contour. All right, now I want to fulfill a promise. I'm reminded of Amazon when I say fulfill. So this is a fulfillment center at the moment. What I want to do is the Fourier transform of a Gaussian, and this is a nice example of a adding a ghost contour. So let me go here and switch the switch to this integral. So the thing we're trying to integrate let's just say that we're originally going to integrate this from minus infinity to plus infinity, e to the minus m squared x squared dx. And so now what I want to show you is that here we're integrating from, let us say, minus capital R. We're taking the limit of the integral from minus capital R to plus capital R along the real axis. So that's the real integral. And now we can imagine adding, now this isn't, I'm not actually adding a ghost contour. What I'm doing is I just am showing you something that's a little bit different. It's relevant for the Fourier transform of a Gaussian. So here, the integral is originally from minus capital R to capital R. And now, suppose we consider this integral, we consider instead a different integral, namely the integral dz e to the minus m squared z squared along this closed contour. Well, we know we should be getting 0 because it's an analytic function and it's a closed contour. On the other hand, we can see that the two integrals, this one and that one, in the limit capital R going to infinity, these two guys, both of them go to 0 because they're approximately equal to, this is a length c, say, the length of that contour is c. So they're basically, the integral is basically c e to the minus m squared capital R squared. And as the limit of capital R going to infinity, this goes to 0. So we can ignore these two In other words, we can say, forget about this, forget about that. And so, but on the other hand, we know rigorously that the integral, the closed integral is 0. And so what does this tell us? This tells us then that the integral dx e to the minus m squared x squared is equal to the integral dx e to the minus m squared x plus ic squared. That's what we learn from the fact that this contour here is equal to 0, which is the contour. Okay. All right. So that's important, and of course the value of this integral. This is a well-known integral. It's square root of pi, and I'm writing pi incorrectly. So let me see if I can undo that and come back to just write it as pi over m. So that's the value of that integral. By the way, as I said, there's a very nice proof of this integration, which is a sort of non-trivial integral. And it's a workhorse in physics, this Gaussian integral. If there's time at the end of the hour, in other words, a half hour from now, and you want me to derive this, I'll show you the very cute derivation that somebody invented 200 years ago, or 150 years ago. I don't know, it must have been 200. Maybe 300, I'm not sure. Anyway, so we can then use this formula to work out the Fourier transform of a Gaussian. So let me maybe do this in successive steps. So I'll switch to black, and so I'm computing f tilde of k, which will be integral dx. Well, I've got, all right, just to follow the notes, I'll use a square root of 2 pi e to the minus I kx minus m squared x squared. So the first thing we do is we complete the square. And completing the square is, of course, super important. We write this as integral dx square root 2 pi. And I want to write this as e to the minus m squared. Let us say, I'm going to call it x plus ic squared. Now, what is c to make this work? And in fact, well, c had better be a k. It had better be a 1 over m squared. And what else? Suppose it's, I think we need a 2. And so then when we take the cross term there, we get e to the minus I k x. All right. But we made a mistake because the c term, the cross term gives us the I kx, but we've added a term. We have to cancel the added term. Well, the added term is minus m squared times ic squared. And so that's just plus m squared c squared. So now we have to write minus m squared c squared. Okay. So this is equal then to e to the minus m squared c squared times an integral dx over square root of 2 pi e to the minus m squared x plus ic, Whoops, that was a C. All right, let me see if I can fix this. Okay, so this is x plus I c squared. But now we've just shown that the integral, this equation in green here, says that the integral of e to the minus m squared x plus I c squared is just the same as e to the minus m squared x squared. And so this is equal then to e to the minus m squared c squared integral dx square root of 2 pi e to the minus m squared x squared. Well, this is the famous integral that we know about. And so altogether, this is e to the minus m squared c squared over square root of 2 pi. And what's the value of that integral? Well, the value of that integral is, where the hell did I have the value of that integral? I had it, well, square root of pi over m. I wrote it down there, so let's hope that that was right. Square root of pi over m. Yeah, there it is, right here, square root of pi over m. So that's the answer, but of course we have to substitute for what c is. So this is equal to 1 over m. The square root of pi's cancel, so we have a square root of 2. And then we have e to the minus m squared, but now c is k over 2m squared squared. And so this is e to the minus k squared over 4m squared. And we divide by m square root of 2. So that's the actual answer, which of course is over here. So this is an example. It's not. It's the example. It's an example of turning a function. Well, I don't know. I'm not sure if it's an example of a ghost contour, because the extra contour we used was not the zero. In fact, it was the negative of the original contour. In any event, one can do various. This Gaussian integral occurs all over physics. In particular, it occurs in the case of deriving path integrals in quantum mechanics or quantum field theory. And so, for example, epsilon here is a time step, or actually it's a temperature step, inverse temperature step, because we're in Euclidean space. And so this integral is just this. And another way of writing this this result is that e to the minus m squared x plus z squared is just just this integral, which is square root of pi over m for arbitrary complex z. So it doesn't matter what z is; it can be real, imaginary, complex, so forth. There are many examples here. I guess I'll do a couple of them today, and some others tomorrow in the 468 class. So suppose we want to compute this integral with a cosine, and so you might originally be spooked because it's a cosine. And what you do is the first thing you do is you realize that cosine is even, and x, of course, x squared is even. So you can expand this to the real line. If you just have the half line, you don't have any, it's hard to add a ghost contour. So we expand this, we say, well, it's 1/2 the integral along the whole real line. Then we write cosine as e to the ix plus e to the minus ix over 2. And we get 2 integrals. And now what we can do is, of course, promote x to a complex variable, and we can add, we add the contour along the upper half plane or along the lower half plane. Now, which do, or around the bottom half plane there. And now which one are we going to do? So let me switch to blue, say. Well, if we look at this thing, e to the iz over whatever, down here it's z minus iq, c plus iq, and we'd be doing dz. And we're thinking of adding a ghost contour of some sort. Well, suppose we are in the upper half plane. Then the important thing is the exponential. This is e to the minus, I'm sorry, get rid of the minus. E to the I, x plus iy. Okay. Now, if we're in the upper half plane, y is positive, and so we have that this is e to the ix, e to the minus y. E to the ix, e to the minus y. Now, e to the minus y, as we go high in the z-plane, upper z-plane, we see that all of this integral is going to be 0. So in other words, this part of the integral is clearly going to be 0. Now, what about this part, the lower part here? Well, the lower part is just a finite distance, let us call it c. And so to estimate that, this is basically just a phase factor. So it is going to be, dz is just the length, so we're going to have roughly c, but then we divide by z squared, but z is r. And so it's c over r squared, and that goes to 0 as r goes to infinity. So in other words, the contour, the ghost contour that we add is this. So let me just show you. The original integral is from minus capital R to capital R, and we're taking the limit capital R going to infinity. And so what we'll do is we'll go up here a distance c, say, and along here a distance c, and then we'll add this half circle. And these two integrals, so let me switch to a different color. This integral and this integral, those integrals are essentially 1 over r squared, which goes to 0. On the other hand, this integral is going to be something like e to the minus y. And y is going to be, well, it's going to be high in the complex plane. And so we could, you see here we've got this going as 1 over r squared. We could arrange to actually, instead of going of length c, we could go of length r here. And then this thing would be r over r squared, would still go to 0. But then this e to the minus, this integral here would be r, would be roughly r e to the minus r, because y is at least as big as r. And so this integral vanishes. To do the second integral, what we do is so we originally have an integral here from minus r to r. Well, once again, we've got, what we do is we go down a distance. Let us go down a distance r. And then we're going to add a ghost contour here, because now what we have is the e to the minus ix term. So this is e to the minus iz over, and this is going to be z minus iq, z plus iq, dz, and e to the minus iz is going to be e to the minus ix plus iy, and that's e to the minus ix times e to the y. So now y has to be negative. That's why we had to go in the lower half plane. And since this integral is this way, this is wrong. It's actually going like that. So let me touch this up a little bit. Okay. All right, so in this case, we add that ghost contour. And so then what we do is we shrink this black contour in the lower half plane, we shrink it to the point wait a minute, where the point minus iq, and over here we shrink the contour to the point iq, and we add the two things up, and then applying, we shrink the contours so they're just going around this way, and this one is going around that way, the wrong way, or clockwise, and we then use Cauchy's integral theorem twice, and we get I pi over 2 e to the minus q over 2iq e to the minus q over 2iq. And so altogether it's pi e to the minus q over 2q. So that's the value of the integral. So let's see, does everybody have sound? I hope so. It's a little late to find out. I might have screwed up. No, I'm unmuted and so forth. All right. Okay, so let's see. Here's an example of third harmonic microscopy. So if you're in either biophysics or optics, you might want to work through that example or ask me tomorrow and I'll do it. Here's yet another example, which is it's almost exactly the one I just did. The difference is we just have one exponent. So we're doing the Fourier transform of k squared plus m squared. And first we factor the denominator and we get this. And then so let's see, if we have to decide what x is. If x is positive, then we add a contour in the upper half plane. So in this particular example, we have an integral e to the I kx over k plus im, k minus im, dx. So that's what we're talking about. Well, except that I said dx, it's actually dk. So this is a k, dk. And now if we say k is equal to, let us say, x plus iy up there in the complex plane. In the upper half plane, we'll have this I, let me undo that last thing. This I times that I will be e to the minus y, so the contour, so what we do is we add this as the contour, and then we pick up the pole at Im. We use Cauchy's integral formula, and we get that for if x is positive, then I of x, which is this I of x, is equal to e to the minus mk. Where's this x coming from? Oh, yes, mx, sorry. There's no k there. We're integrating, so, all right, hold on, I've got to undo something. So it's k is equal to Im, so ikx becomes minus mx. And then using Cauchy's integral formula, we get that this is, oh, well, let's look at the denominators then. We're setting k equal to Im, which is, so that this thing is the pole. If k is equal to Im, this is 2Im, so that's 2Im. And the rest of it then is 2 pi I, and so altogether the 2's cancel, the i's cancel, we get pi over m e to the minus mx. This is for x positive. For x negative, let me switch maybe to blue. For x negative, once again, I of x is equal to integral e to the ikx dk. And again, k plus Im, k minus Im. Now we add a contour. We're integrating from minus infinity to plus infinity like that. We add a contour here, and we pick up the pole, this pole here, at minus Im. And so that gives us 2 pi I e to the, let us see, k is equal to minus Im, e to the mx, and we're dividing by minus 2Im. And so this gives us the 2's cancel. We get a minus sign, minus pi over m e to the mx. And all right, I did something wrong. The integral is clockwise rather than counterclockwise, so we have an extra minus sign here. This means a plus. So we get, for negative x, we get this result. And so the actual value of the integral, which is the integral from minus infinity to plus infinity of dk, in other words, it's this Fourier transform, e to the ikx over k squared plus m squared, is then equal to pi over m e to the minus m absolute value of x. Okay, we have only about 6 minutes left. Is there another question or a question? Or let me go a little bit further with this because this, well, actually, this is kind of, this is more than a little, this is a little bit, it's interesting, it's worth, if you're interested in these things, work through it or ask me tomorrow. I don't think we should do it right now. If we're doing this, let us suppose we're doing this in 3 dimensions. So we have a 3-dimensional Fourier transform of essentially the same thing. Then we go to spherical coordinates in K. We take the z-axis in K as being in the x direction. We have x fixed here. So we write k dot r as kr cosine theta. The integral of the phi integral gives us a 2 pi, which brings us to 2 pi squared. We then have a d cosine theta. In other words, we have sine theta d theta. That's minus d cosine theta, but the sine theta goes from +1 to -1 in cosine. And so since we want to go from -1 to +1 in cosine, we cancel the minus sign, and we have this expression. And so we have this d cosine theta here. Well, cosine theta is just a variable. You can call it q or something. So we have e to the I k r q dq, and that just means that we have to divide by I k r. So that, and then we have e to the I k r minus e to the minus I k r. One of the the I r pops out here. The other k changes k squared to just k, and so we have this. And now we can see that these two things, if we can combine them into a single integral from minus infinity to plus infinity, and so that is, and if we factor the denominator, we have this. Well, we can add a ghost contour now. R is always positive, and so the ghost contour will always go over the upper half plane, and then we just repeat the previous analysis, and we get, we pick up the pole at k equal to im. So here, if I say switch to a different color, what we wind up with is we started having this integral, we add the ghost contour, we pick up the pole at k equal to im. So this is the ghost contour. And we then close the contour and use Cauchy's integral formula. And I've got 2 minutes left, so maybe I'll do this explicitly. So we have then g sub y of r is equal to 1 over IR integral dk over 2 pi squared k over k minus im k plus im. So this just becomes 2im because we're integrating, we shrink the integral around this, or equivalently, we just use Cauchy's integral formula. And then we have e to the I k r. So basically, we just replace, this is the 1 over z minus z0 term. And so we just get that the whole thing is 2 pi I times all this evaluated at k equal to im. And so we have, first of all, 1 over IR, 2 pi squared. This would be 2im. The numerator there would be im. And then we have e to the minus mr. And so altogether we have a, let's see, 2 here, 8 down there, so we have 4 pi r. the i's canceling, the m cancels, e to the minus mr. And this, of course, is the Yukawa potential. This is called a Yukawa potential. And it plays a big role in nuclear physics. Yukawa proposed it when the mu meson, it's not a mu meson, the muon was discovered, which is a heavy electron. In fact, it's an electron that's a negatively charged particle that's 200 times the mass of the electron. So he proposed then this formula and proposed it as important in nuclear physics. And the reason he proposed it as important in nuclear physics is that it was known at that time, sometime in the 30s, that nuclear forces were short range about, well, 1 Fermi, which is 10 to the minus 15 meters. And the muon had a mass of 105 MeV. And so he said, well, there it is, that's the particle. But it turned out that the muon has nothing to do with strong interactions in nuclear physics, as far as we know. And the particle that actually is used in nuclear physics and plays an important role in nuclear interactions or low energy strong interactions is the pion, which has a mass of 140 MeV, which isn't that different from the muon mass, but the pion does interact with nuclei in a very strong way, and it's a short range interaction being bounded by e to the minus mr. By the way, in this integral and in many of the formulas that I'm comfortable with, I set h bar and c equal to 1 because they then don't clutter things up. And the other problem is that if I want to then translate this into something that makes actual sense, I have to figure out what is how do I add h bars and c's? Since h bar and c are equal to 1, I can sprinkle them into any formula until I get the units right. And so what we want is mr to be dimensionless. And so let's see, suppose I take mr and I multiply by c squared. Now I've got mc squared times the distance. Now, if I divide by h bar, that's an energy times a time. And so now I've got too many times in the, I probably should divide by a c. So now h bar c is, has units of energy distance. And so now this thing is dimensionless. And so this thing is e to the minus mr c over h bar. If I haven't made a mistake, that's right. Okay, we're out of time. And some of you guys want to watch the debate. I know I do. I've got my Biden mug here and I'm rooting for Joe. And so I'll see you all tomorrow at 5:30, and I'll end the thing now. Thanks for listening and so forth. So let me end the recording. Actually,
have a good night. Thank you.
Yeah, you too. Stay safe. Stay out of bars, for God's sakes. So in